Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the concepts of type 1 error, type 2 error, and power. To recap, we don't have access to the population, or reality. Yet we are going to try to infer things about reality and the population from our sample and make a decision about the null hypothesis. So we'll either reject or we'll fail to reject the null hypothesis. We aren't going to know if we made the right decision. We could have made the right decision, but we could have made the wrong decision about the null. Here are three important concepts related to this choice in the context of significance testing. Type 1 error is the probability of rejecting the null hypothesis when it is actually true. This is making a decision that there was an effect in the population when there actually was none. Type 2 error is the probability of failing to reject the null hypothesis or retaining the null hypothesis when it is actually false. This is the probability of determining that there was no effect in the population when actually, in reality, there was an effect in the population. Power is 1 minus type 2 error, and this is the probability that we correctly reject the null hypothesis. In other words, power is the probability that we determine that there is an effect in the population, and in reality, there is an effect in the population. So as we're learning, there's a chance we could be wrong in our decision to reject or to fail to reject the null hypothesis. And there are two ways that we could make this wrong decision. So these are type 1 error and type 2 error. The type 1 error is denoted with alpha, and type 2 error is denoted with beta. An example of type 1 error, using the last lecture's example about teacher boldness, would mean that there in reality is not a difference between our teacher's boldness mean and the population mean of 0. But we mistakenly reject the null hypothesis and conclude that we did increase teacher's boldness with our intervention. The researcher actually gets to control the type 1 error by deciding on the significance level, and we'll talk more about that soon. So on the other hand, type 2 error is not rejecting the null hypothesis or retaining the null hypothesis when it is actually false. So in our teacher boldness example, this would mean that in reality, there is a difference between teacher's boldness mean and the population mean of 0, and you miss it and you retain the null. In other words, in reality, teacher's boldness mean would be different from 0, but we retain the null hypothesis that the boldness mean is 0 and think that we didn't increase teacher's boldness with our intervention. Power is the ability to reject the null when it's really false. In other words, it's the probability of detecting a false null hypothesis. And in the teacher's boldness example, this would mean that there is a difference between teacher's boldness mean and the general population mean, and you correctly reject the null hypothesis. So what we see in this figure is a sampling distribution of means from this teacher boldness example. Recall that in our example, the null hypothesis was that the mean of teacher boldness was equal to 0. 0 is the mean value for the general population of teachers. To illustrate the concept of type 1 error, we are going to say that the null hypothesis is actually true in reality. So in other words, the mean of teacher's boldness is in fact equal to 0. In other words, our intervention did not work to increase teacher boldness. However, when we drew our sample, something influenced our results, and our teacher's boldness mean happens to be higher than it is in the population. The sample mean, here it's shown as 4, was far enough away from 0 that we decide to reject the null hypothesis. In this situation, we would have committed a type 1 error. So by rejecting the null, we have said that there is a difference between the teacher's boldness mean and 0, when there isn't really a difference. In this context, we would have concluded that our intervention worked and increased teachers' boldness, but in reality, it did nothing. So there is another scenario that may happen given the null hypothesis is true in reality. Rather than making a type 1 error, we could make the correct decision to retain the null hypothesis. Again, what we see in the figure is a sampling distribution of means for boldness. And recall that in our example, the null hypothesis is that the mean of teacher boldness is equal to 0. So we are going to say that the null hypothesis is actually true in the population. In other words, the mean of our teacher's boldness is in fact equal to 0. In our sample, after we gave the intervention to our sample, let's say that we observed teacher's boldness mean as just slightly lower than in the population, at negative 0.2. The sample mean was close enough to 0 that we decide to retain or fail to reject the null hypothesis. In this situation, we have correctly retained the null because we have said there is no difference between the teacher's boldness mean and 0, which is consistent with reality. In this example, we concluded that the intervention did not work, and we were correct in saying that. Type 2 error is the probability of retaining the null hypothesis when it's actually false in reality. Now, in this figure, there are two sampling distributions of means for boldness. The curve on the left is what the sampling distribution of means would look like if the null hypothesis were true. Its mean is at 0. The curve on the right is what the sampling distribution of means would look like if something other than the null were true. The mean of boldness is not equal to 0. Specifically, in this sampling distribution on the right, the population boldness mean is equal to 4. In this figure, you can ignore the shaded part. To illustrate the concept of type 2 error, we are going to say that the null hypothesis is actually false in reality. In other words, the mean of teacher's boldness is in fact not equal to 0. Let's say it's actually equal to 4. When we collected our data, something influenced our results, and our teacher's boldness mean was reported as lower than what it was in reality. So in our sample, we calculated the teacher's boldness mean as 1. The sample mean was close enough to 0 that we decided to retain the null hypothesis. We have committed a type 2 error. By retaining the null, we have said that there is no difference between the teacher's mean and 0, but really there is a difference. In reality, it's 4. So in this example, what this means is our intervention may have actually worked and increased boldness to a 4, but we missed it and we retained the null hypothesis. In a type 2 error, you had a significant result, but in reality, you missed it. And I had trouble keeping type 1 and type 2 error straight during my undergrad. So I'm hoping that this Research Wahlberg meme from Twitter will help you remember. The best you never had means that there was never an effect to begin with. Here's another meme explaining the difference between type 1 and type 2 error. In the first picture, the doctor is telling this man that he's pregnant. This is a false positive. This man biologically can't be pregnant. So this is a type 1 error. In reality, there's no effect, or no baby, but the doctor is telling this man that he's pregnant with a baby, a false positive baby. On the right, this woman is clearly pregnant. We can see that visually. And this doctor is measuring the heartbeat of the baby and telling her that she's not pregnant. This is a false negative. So in reality, there is an effect, but the doctor is telling her that there is no effect, in reality, there is a baby, but the doctor is telling her there is no baby. So it's a false negative baby. There's one last scenario that may happen given that the null hypothesis is false in reality, or that there is some effect in reality. Rather than making a type 2 error, we could make the correct decision to reject the null hypothesis. Again, what we see in the figure are two sampling distributions of means for boldness. The curve on the left is what the sampling distribution of means would look like if the null were true and its mean is at 0. And the curve on the right is what the sampling distribution would look like if something other than the null were true. Here again, the boldness mean in reality is equal to 4. And again, ignore the shaded part. So we are going to say that the null hypothesis is actually false in reality. In other words, the mean of teacher's boldness is not equal to 0. It's actually equal to 4. After the intervention on our sample, our teacher's boldness mean that we measured was far above 0. So let's say in our sample, the boldness mean was 3. The sample's boldness mean was far enough from 0 that we decided to reject the null hypothesis. We have correctly rejected the null because we said that there is a difference between our teacher's boldness mean and 0, which is consistent with reality. So in this example, we have made a correct decision to reject the null hypothesis. We did not make an error in our decision. So hopefully everyone now understands that type 1 error is the probability of rejecting the null when it's actually true, and type 2 error is the probability of failing to reject the null when it's actually false. But we haven't talked about power much. So statistical power is actually my favorite topic. It's one of my areas of research. Type 1 and type 2 error are related to us making a mistake in our decision regarding the null. In contrast, power is the probability that we correctly reject the null. So in other words, the null hypothesis is false in reality, and we make the correct decision to reject it. Some people also call this sensitivity. Power is directly related to type 2 error. It is 1 minus type 2 error, or 1 minus beta. That makes sense because type 2 error is the probability that we fail to reject the null when it is actually false. And power is the probability that we reject the null when it is actually false. We can't directly compute the probability of type 2 error or power because that requires knowing certain population parameters. However, we know what factors influence power. We can set alpha, and we usually set it to 0.05. If we increase alpha, that is, we would accept a higher chance that we reject the null when it's actually true. We decrease beta. So simultaneously, there is a greater chance that we retain the null when it's really false. If alpha is higher and beta is lower, we have higher power. But we would also accept a higher level of risk of being wrong in the direction of a type 1 error. In addition, when we have a higher sample size, we have higher power. Why is this? Well, when we have higher sample sizes, the standard error of the sampling distribution decreases. In other words, the sampling distribution becomes narrower. This results in less overlap of the distributions for the null and alternative hypotheses. The beta region becomes smaller and the power increases. In addition, magnitude of the difference between the means under the null hypothesis and the true mean under the alternative hypothesis matters for power. This is effect size. When they move farther away from one another, you will have higher power. The beta region becomes smaller and the power increases. For your viewing pleasure, another Research Wahlberg meme that's a pretty ridiculous pun. I usually hate puns, but I think they're okay when they're about statistical power. This concludes the lecture on type 1 and type 2 error and power. In the next lecture, I'll describe significance levels.